And welcome back, students, as we continue our discussion on recursion. Let's today discuss how to think recursively as we examine our efficiency of our binary search algorithm from our last lesson. So getting started, the binary search algorithm is extremely fast compared to an algorithm that simply tries all array elements in order. So in the binary search, you eliminate about half the array from consideration right at the start. And then you eliminate a quarter, and then eighth, and so forth. All right, so for example, if you have 100 elements in the array, you automatically right off the bat say, well, I'm not going to check all 100, I'm going to check 50. These savings can add up to a dramatically fast algorithm. So for an array of 100 elements, binary search will never need to compare more than 7 array elements to that of the key, based upon how it's cutting it down. Now, serial search means going one after another. It would compare as many as 100 elements to the key, and the average will compare about 50. So, worst case, it's going to do all 100, but on the average, it's going to be 50, about the halfway point. Whereas like you compare that to the 7, that's a pretty drastic difference. In fact, the larger your array is, the more dramatic your savings are going to get. On an array with 1,000 elements, the binary search is only going to need to compare about 10 array elements to the key value, as compared to the average of 500 for the serial search. And this is because the binary search algorithm has a worse running time that is logarithmic, or big O of log n. If you compare this to the serial search, which is going to be big O of n. And we'll look at what big O means in a couple minutes here. So let's go back and just for a second, if we think about our algorithm here, we have an iterative version that we could create. All right, and I'll put that up in the class materials for you to look at. Now, in some systems, the iterative version will run more efficiently than that of the recursive version. The algorithm for the iterative version was obviously derived by mirroring our recursive version that we looked at last time. In the iterative version, the local variables first and last mirror the roles of the parameters in the recursive version, which of course are named first and last. And as the example is going to illustrate, it sometimes makes sense to derive a recursive algorithm, even if you expect it to convert it later to that of an iterative algorithm. Remember, sometimes the recursive algorithms are easier to write. All right, next we have what's known as tail recursion. Now, most modern compilers will convert simple recursive method definitions to that of an iterative one before running the program. A method that uses tail recursion has the property that it does nothing after the recursive call except return the method value. In this case, a tail recursive method can be easily converted to that of an equivalent iterative solution. Now, you as the programmer don't actually have to worry about much of this. This is something you just need to know in terms of how the recursion works, because this is actually performed either by your compiler or by the Java virtual machine. You don't actually have to worry about that. All right, so I said we would talk about big O, and here it is. You can see we have this nice, beautiful graph here showing some of the different big O notations. So big O notation is one of the measurements of how efficient an algorithm is. The faster the curve grows, the worse the algorithm. So obviously, big O of n to the power of n, so it'd be something like big O of 2 to the power of n, is a exponential function. It's really, really terrible here. But if we look here at like some of these other ones, you can see that their graphs aren't quite as drastic. We have a cubic, a square. This would be n to the 1, or a linear function here. We have our square root, we have log n, and then we have 1. Big O of 1 is technically considered to be an ideal function, as it means that the time to solve is constant regardless of data size. So if I have 100 elements or have 1 million elements, it doesn't matter. The amount of time for it to process the data is always going to be big O of 1. All right, now let's look at this with an example, which is in this case is called finding a file. So the next program is an example where a recursive solution is easier to write and understand than that of the iterative version. So consider the problem of trying to find a file buried somewhere in your file system. So for example, using the Windows file system, let's say you have the following file and directory structure in your hard drive. So on your C drive, you have like Java programs, you have papers and letter.txt on the first level. Inside of Java programs, you'll have 2 folders, recursion and homework, another file called test.java. Inside of recursion, findfile.java and binary search.java, etc., etc. So let's say we want to find the location of a file given its name. So for example, given term paper.odt, we'd like to know that it's located in C:/papers. All right, simple enough. If we're given find file.java, we'd like to know that it's located in C:/Java program/recursion. The general solution, when we look at these, is to start some root directory, such as the C drive, and then to go through all the items in the directory. If an item is a file, we'll check to see if it matches the target. If it's a directory, Well, then what we want to do is make a recursive call to restart the search using that directory now as the new root directory. So a quick pseudocode of how a recursive solution should look. So we're going to search for a file based upon the current path in the target file. If current path is not a directory, return an error. For every item in the current path, if that item is a directory, R is search for file, I target file. If R is a successful match, return R. If I is a file, we're going to check to see if it matches the target file. And then if so, we're going to return the path to the file. Otherwise, return target not found. All right, so to implement this algorithm, we need a way to determine if a path is a directory or a file. And we need to find a way to get all the items within a directory. Java's file object will do all this for us. To use it, we simply just import java.io.file. Now here are the relevant constructors and methods. So we have the file constructor, which we just do a string path name, string get absolute path, string get name, a boolean is directory, and file is files. So the first one is simply just a constructor which is going to pass the file name and creates a file object with the corresponding file or directory. The get absolute path is what actually gets us the path name of the file object. Get name is what would return just the name of the object. The boolean simply just returns true if it is a directory. If it's not a directory, obviously it's going to return false. And then with our file list files, it's simply just if the file object is a directory, then this is going to return an array of the file objects corresponding to all the items within the directory. So using the file object, we can implement the recursive algorithm in order to find that file. The implementation of find file returns an empty string if the target file is not found. If the initial root folder supplied is not a directory, then an error message is returned. The sample results will then assume the program runs the directory structure shown on the prior slide. Alright, so let's go ahead and take a look at that and see how that would actually work. So here is my actual program here. And in here I have string result, and I have it set to just a empty string. Then we have our directory.is directory. Of course, dir is our file object right here. Return path is not a directory. Then we have our recursive part right here. So in here, if we look, we say for file folder item directory.list files. It's going to recurse if it is a directory. So this is the recursive call. It says folder item is directory. Result equals search for file. Folder item.target. All right. So right in here, this is the recursion right here. That's the recursion right there. Now, in here, it's going to look to see if the result does not equal nothing, return results. All right. Then once it gets down, it's like, okay, well, if it's not going to do that, because remember, it's going to recurse and do the whole thing over again. It's going to say if folder name.get name equals target, return folder item.get absolute path. So this is going to get the absolute path here. Otherwise, blah, 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 blah. It keeps going until everything falls out, and we get right here, return nothing. Now, down here is our main method. So this is how we actually execute the code. So file, folder equals new file. Now, you'll notice in here, I have a N, not a C like I had in the notes. That's because one caveat you have to do with this is when you do this, you have to make sure it's going to be in the same directory as with the file. So if you, let's say, want to search for a file on the, let's say in your downloads folder, then you need to make sure that this find file program is in the downloads folder, or it's at least on your C drive. If it's on the C drive, it should be able to find it. But if you put it on something like the network drive or your N drive, it's technically a different drive and it may not find that file. Right? And so I made a little note here that's changed to the path file of where you want to search. All right, that result is equal to space, print out the results, otherwise print out file not found. All right, so let's just go ahead and give this a quick run here. And you'll notice it seems right now to be hanging. However, it's not necessarily that it is hanging. All right, it simply it has to search through it. Once it finds that file, you'll see it prints it out right here, n/findfile.java, and that's it. All right, that's how the program works. So it might, if you see it just sitting there, don't panic. It just hasn't completed its search. All right, and that's going to wrap this notes up for today, folks. So until next time.